Okay, so we talked about ionic bonding. Now we're going to talk about covalent bonding. The difference between ionic and covalent is with ionic bonds, you have a metal which gives electrons away, and you have a nonmetal which takes them. So when you give electrons away, you form a positive ion. When you take electrons away from somebody, you now have more electrons than protons, and you have a negative ion. Covalent bonding is between two nonmetals, generally. And when you have two nonmetals, they're each capable of stealing electrons away from metals. But generally, they're not capable of stealing electrons away from other nonmetals. So what do? They can't steal the electrons to make ions. What do? They share. Oh, they share the electrons together to get them to an octet for stability. So the first example we're going to look at is just very simple, the simplest compound there is, hydrogen. Now, instead of taking electrons away from each other, one of them becoming positive and one of them becoming negative, they only have the one electron. And so what are they going to do? What they're going to do is share each other's electrons in order to get two. So this hydrogen has one electron. This hydrogen has one electron. Now, if they share that electron, they each now can say they have two. So remember, we go back to the s orbital. Since hydrogen is in the first row, it only has the first energy level. And in the first energy level, there's only s. One s. And in s orbital, if you remember, there's only room for two electrons. That's it. There ain't no more. And so one hydrogen has one electron. The other hydrogen has another electron. But if they share them, each of them now has two electrons in a shared orbital between them. And so now they look like helium, who also has two electrons in its first shell. And that is a complete, remember, only for the first row, hydrogen and helium. Once you get to the second row, we add a new subshell and we add more electrons, generally to 8, an octet. Now we show these different elements and how many electrons they have to share, that is, valence electrons. We use what's called an electron dot symbol, or a Lewis structure, invented by Professor Lewis, who was a long-time chemistry professor at UC Berkeley and was nominated for a Nobel Prize at least 8 different times, but the poor man never won it and actually died at his bench doing chemistry. So he was a hardcore chemist. So the electron dot symbol for any atom just has the elemental symbol, in this case hydrogen, and we put a dot next to it for the excuse me, for the valence electron. So for hydrogen it would just be an H and one single dot, which gives you the number of valence electrons. Okay? Now, to make covalent bonds, each element tries to complete its octet by sharing electrons with another atom. So those electrons need to be unpaired. And that'll become super, super important. Because remember, when we were looking at orbitals, all the electrons paired together, right? One was spinning up, the other was spinning down. And so when they're paired, they achieve stability. When they're unpaired is when those electrons are the ones that get shared. So a shared pair of electrons is called a bonding pair. And we represent those as a line between the two elements. Now let's look at the two elements forming a bond here. These are chlorine atoms. And each chlorine atom has 7 electrons. So if it has 7 electrons, let's look and see what they would look like. Let's make the electron dot structure of chlorine. So chlorine, I go 1, 2, 3, 4, 5, 6, 7. So that's 7 electrons. Notice that these two are paired, these two are paired, these two are paired, this one is not. That is unpaired. And so chlorine basically has that 1 electron that's unpaired, and it's going to share that 1 electron with another chlorine that looks exactly the same, also with 6 paired electrons and 1 that's unpaired. So here is the unpaired electron for chlorine number 1. There's the unpaired electron for chlorine number 2. So they share those pair of electrons, and that forms a covalent bond. The other electrons are paired up, so they're not going to be shared. Even though chlorine has a lot of electrons in its outermost shell, if they're already paired, not going to share them. That's why chlorine just has chloride ion, just has a -1 charge. It just takes the 1 electron in from a metal, and then it's full, right? Then it has a full octet. Same thing when it's forming covalent bonds, when it's sharing electrons. It's only going to share that 1, because then when it shares that 1, it also has a complete octet. It has 8 electrons. And so it then is as stable as the next element to chlorine. And if you remember from the periodic table, the element next to chlorine is up here. Chlorine is here, and right next to it is argon. So it appears chemically to look like argon. Very, very, very stable. So let's look at probably the most important element for organic compounds and biochemists and everything, carbon. Carbon, super, super important for biological material. Carbon is in which group? Group 4, right? So it has 4 valence electrons. Let's draw them. So here's carbon. 1, 2, 3, 4. Now notice when we draw carbon like that, we go in a circle. We go around in a circle. And since carbon has 4, notice that all of its electrons are unpaired. All of them. So how many bonds does it make? Same number as it has unpaired electrons. 4. So it can do it in a variety of different ways. It can form 4 single bonds. If it shares each electron with an adjacent atom, it can form 4, are called single bonds. Or it can share 1, 2 electrons with an adjacent atom. And if it shares a pair of electrons with an adjacent atom, that's a double bond. Or it can share 1, 2, 3 atoms or electrons with an adjacent atom. 3 electrons shared give you a triple bond. And in each case, carbon then has 4 bonding pairs. 1, 2, 3, 4. 4 pairs of electrons is 8. So that gives you an octet. And if you're asking yourself, how come I can't form a quadruple bond? I don't see a quadruple bond here. Well, we'll see when we look at the shapes of molecules a little bit later that it's basically impossible to get 4 electrons all squished over to one side. There's no room. And so the most bonds it can make on one side is 3. Okay, we'll deal with this a little bit more in a minute. So these are the main group non-metal elements for 4, 5, 6, and 7. Now remember, these are non-metals, and so you're going to be taking electrons, but they can't really take them from each other because they're all strong at pulling on electrons, so they wind up sharing them. So when we draw their electron dot structures, hydrogen we've already done. Hydrogen just looks like this, single dot. But when we look at carbon, carbon has 4, and we looked at carbon, and we draw them like this. Remember, we go 1, 2, 3, 4. They keep disappearing on me. So that's 4. So we can see from that that carbon can make a variety of different sharing groups. It can share 1 to 4 different atoms to make single bonds. It can share 2 with an atom on one side to make a double, leaving 2 single bonds, or it can share 2 electrons on one side, 2 electrons on the other side to make 2 double bonds. It does that when it makes carbon dioxide. That's what carbon dioxide looks like. Or it can form a triple bond on one side and a single bond on the other. So that's carbon. 4 valence electrons, 4 of them available for sharing. But when we move next to nitrogen, what happens when we substitute nitrogen with its 5 valence electrons instead of 4? Let's take carbon out of there and put in nitrogen. So now I've got nitrogen. And I add 1 more electron. Now I go around in a circle. So I've gone around in my circle. So I got 1, 2, 3, 4, and now I put my 5th one here. Notice that now it looks different in an important way, because this is a pair of electrons. And paired electrons don't get shared. Why? Because every atom wants to pair their electrons. That's the whole point of making bonds. They want to pair those electrons. Well, nitrogen already has 2 of its electrons in pairs. So it's only going to form 3 bonds. So, and it can do it in a couple of different ways. It can form 3 single bonds, like it does here. It can form a double bond on one side and a single bond on the other, like it does here. Or it can form a triple bond on one side, leaving a lone pair of electrons on the other, like it does here. And actually, it can form 4 single bonds sometimes. If it gives one of its electrons away and becomes positive, then it has 4 valence electrons and can do this. 1, 2, 3, 4. But that's when nitrogen is a positive ion, not a negative ion, not an atom. If it's an atom, it has 5 valence electrons. If it's an ion, it has 4 valence electrons. Okay? So what if now we move to oxygen with 6? So oxygen, we put an O in the middle, and then we put the dots for electrons around it. We go 1, 2, 3, 4, 5, 6. So I've got 6. Notice that now that I have 6 electrons, I have 2 pairs. This one is paired, these 2 are paired, and it makes 1, 2 bonds. So oxygen can either make 1 double bond, like it does here, by sharing both those electrons, or it forms 2 single bonds, 1 on one side and 1 on the other, like water. Then when we add an additional electron, now we've gone from 6 valence electrons, now we have 7. Those are the halides: fluorine, chlorine, bromine, iodine. Let's draw what that would look like. So I'm going to draw fluorine this time. So we put fluorine. Here's our fluorine. 1, 2, 3, 4, 5, 6, 7. Now notice it has 7 electrons and 2, 4, 6 of them are already in pairs. So how many bonds do you think fluorine's going to make? That's right, just one, because it only has the one unpaired electron, and only unpaired electrons get bonded, okay? So since carbon has no paired electrons, it has 4 unpaired electrons, it makes 4 bonds. Nitrogen has 3 unpaired electrons, it makes 3. Oxygen has 2 unpaired electrons, it makes 2. Fluorine only has 1 unbonded electron, it makes 1. Okay, that's how we can always figure out from the Lewis structure how many bonds each of these atoms is going to make. Lewis was a pretty clever guy. So let's look at formulas and structures of some of these things. So a molecular formula for a covalent compound gives you all the components in a molecule. The difference between a covalent formula and an ionic formula is that molecular formulas for covalent compounds don't reduce to the smallest whole number. For instance, if I have calcium 4, fluorine 8, that is, I have a metal and I have a non-metal. That's an ionic compound. So the simplest formula that gives me a net charge of 0 is I reduce each one by a factor of 4. So I get calcium fluoride is actually CaF2. That's the smallest number that gives me a net negative charge of 0. Molecular formulas don't do that because there's a lot of different ways that these atoms can share electrons. Like I just showed you, carbon can share electrons. It can make double bonds, it can make single bonds, it can make triple bonds. So when you have a molecular formula for a covalent compound, all those atoms are present in the number given. So glucose has this formula, C6H12O6. I can't reduce that to CH2O because that's not the formula for glucose. Glucose has 6 carbons in it, not 1. So I can't reduce those. Ionic, I can, because I just need the simplest number of charged elements that give me a net charge of 0. Since there's no charge in covalent compounds, and they can be put together in all kinds of bizarre ways, I have to have each one of those elements there and exactly the number that's given, okay? So let's look at a very simple covalent compound, methane, basically the main component of natural gas. So methane has this molecular structure of CH4, all nonmetals, carbon and hydrogen, although hydrogen can be a metal sometimes under weird circumstances. So carbon makes 4 bonds, as I've shown you. It has 4 unpaired electrons. Hydrogen has 1 unpaired electron. So each hydrogen shares its 1 unpaired, it's only got a single electron, shares that electron with an unpaired electron in carbon. So now it forms those 4 single bonds. So now carbon has a pair there, a pair there, a pair there, a pair there. It's got 4, now it has 4 paired pairs of electrons in its outermost shell. And hydrogen has 2 because they're sharing them. So hydrogen has 2, it's happy and stable. Carbon now has 8, it has 4 pairs of electrons, it's happy and stable. We call this a Lewis structure, and we would write it like this. Notice there's no unpaired electrons, so there's no dots. Carbon doesn't have any unpaired electrons, they're all paired. Hydrogen doesn't have any unpaired electrons, they're all paired. They're all being shared. Carbon's electrons are all being shared. So there's no lone pairs that aren't being shared with somebody. So we just write it like that. Now, if you look at it, you would think that would be a flat structure because we're writing it in 2 dimensions. It looks like a flat structure, but we'll learn that it isn't flat at all. Let's draw a Lewis structure for each one of these covalent compounds. So I'll give you, you can pause, give you a second. Okay, so NH3, that is actually ammonia. That really, really strong smell from ammonia, that comes from nitrogen having a lone pair of electrons. Believe it or not, it's true. So when you get a Lewis structure like this, the central atom will generally be on the left, and the atoms that go around it are generally on the right. So NH3, that gives us a nitrogen in the middle, and 1, 2, 3 hydrogens around it. Now each one of them, since these are covalent bonds, we put a line in between them. So it has 1, 2, 3 covalent bonds. But remember, what did nitrogen, remember what nitrogen looked like when we looked at it next to all the other atoms in the first row? Nitrogen makes 3 bonds and has a lone pair. So we have to put the lone pair in there. That's why it doesn't make 4 bonds, because it already has a pair of electrons bonded. It already has a pair of electrons that's completed as a pair. It doesn't need to share them with anybody. So that would be the Lewis structure for ammonia. And like I said, when nitrogen has a lone pair, you get that really strong smell. That really strong fishy smell comes from nitrogens in a molecule with unpaired electrons, with unshared electrons. Very, very nasty. All right, let's look at the next one. Next one's a little trickier. So we look at this one. We've got 2 carbons and 4 hydrogens. Now, already I look at this and you say, how is that going to be arranged? You think of the number of bonds each one of them can make. Hydrogen can only make how many bonds? It's only got 1 electron, it can only make 1. So those 2 carbons have to be bonded to each other. So this is what the central structure will look like. Carbon bonded to another carbon. Now, where are the hydrogens going to be? They're going to be around the 2 carbons. So 1, 2, 3, 4. And we give bonds to each one. 1, 2, 3, 4. So now I'm looking at this and I'm thinking something doesn't quite look right. What's wrong? The answer is the number of bonds in the carbon. Now remember, how many bonds does carbon make? That's right, it makes 4. Each carbon has 4 unpaired electrons. So it's going to make 4 bonds. And in this structure, it's only making 3. Where's the other bond? Well, the other bond is between the 2 carbons. So it's making a double bond between the 2 carbons. We'll learn that this is called ethene. It's called an ene when you have a double bond, an ane when you have no double bonds, and an ine when you have a triple bond. We'll get to that a little bit later. So that gives each carbon 4 bonds. Why can't the hydrogens make a double bond? They only have a single electron, so they can't do it. Hydrogen cannot go in the middle of a compound either. Why? It can only make a single bond. So when you have carbons, nitrogens, oxygens, sulfur, phosphorus, those generally go in the middle of a compound because they can form more than 1 bond. Hydrogen never goes in the middle because it can only form 1. Okay? Now, when you're coming up with a molecular formula is just a complete chemical formula for a covalent compound. Now remember, covalent compounds can be really complex with single bonds, and double bonds, and triple bonds. So we can't basically reduce them to the lowest common denominator because they're not ions. They can't just be simply canceling out charges. So what we want to do, so when we name them very similarly to covalent compounds. We usually put the more metallic or the element that's further to the left on the periodic table. We put that first, and then the one that's a little bit further to the right, the more non-metallic element, we put that one second, not always, generally. But the second one also gets the same suffix. We used "-ide" before, we use "-ide" again. Now the big difference here is we don't always know how many of the compounds are going to be, how many elements are going to be in each compound. With an ionic compound, if I write calcium chloride, I know there's going to be one atom of calcium because it's +2, and I know there's going to be 2 chloride ions because they're both -1, and that balances out. But when a covalent compound, there could be a whole bunch of different numbers because I don't know how they're bonded together. There's a variety of different ways they can bond together. So what do? So in order to figure that out, we actually say in the name how many atoms there are. Like we use these prefixes. We use the Greek prefixes. Mono, di, tri, tetra, penta, to say how many different elements there's going to be. Like for instance, if I say carbon oxide, you don't know whether I mean carbon monoxide with just 1 oxygen, or do I mean carbon dioxide with 2? You don't know. It could be either one. So in order for me to convey that information to you, I would have to say carbon monoxide. That means C. If I just say carbon without more than, if I don't say dicarbon or tricarbon, just assume there's one. Monoxide means a single oxygen. That's carbon monoxide. Big difference between carbon monoxide and carbon dioxide. If you breathe in too much carbon monoxide, it'll kill you a lot faster than breathing in carbon dioxide will. So carbon dioxide tells you di-2 means 2 oxygens. And then some compounds generally known by their traditional names. Like we don't call water, we could call it 2 hydrogens. We would call it dihydrogen oxide or dihydrogen monoxide, but that's a mouthful. So we just call it water. And then nitrogen three hydrogens, trihydride, no point. It's been known as ammonia for like thousands of years. So we just call it ammonia. But if you want to get fancy, you could call it nitrogen trihydride. So these are the prefixes we use. So 1, mono, 2, di, tri, tetra, penta. We generally, I mean, these are also in the table, the test table. So you don't have to memorize these. But it's good to know them. I mean, you're probably familiar with most of them. It's not till you get up to like penta, hexa, hepta, up to those. But generally, the most common ones you'll find are mono, di, and tri. Sometimes tetra. Very rarely will you use 7, 8, 9, and 10. You don't see a lot of super complex binary covalent compounds. Binary meaning 2. If there's only 2. If you have something really complex like sucrose or something, we don't give it an insanely long name. We just use the simple name for that. So let's write the name of each one of these compounds. I'll let you pause it for a second, and then we'll come back. All right, so the first one, it has 1 carbon and 4 fluorines. So we would just call that one carbon. Tetra for 4, fluoride. So carbon tetrafluoride. Second one, we have Se. What's that one? Selenium, right. So we have just a single selenium. So we just say selenium. And there's 2 chlorines, so that would just be dichloride. And the last one, S is for sulfur, right? So that is just sulfur. You can also use a pH instead of an F for sulfur. Trioxide. Remember, use the same ide. So fluoride, oxide, nitride, chloride, IDE. You just have to give the number because all the different ways that the electrons can be shared in either double, single, triple bonds. It's impossible to guess what the ratio of these elements are. You have to be clearly told what they are. So let's look at some of the characteristics of covalent bonds. This is where you really interesting part of chemistry, where you learn that the shapes of the molecules are really, really important for how they react chemically and physically. So we're going to learn about something called electronegativity. I've sort of vaguely referred to it a little before. That is the ability of an atom to pull on shared electrons. So if 2 elements are sharing a pair of electrons, one of them generally is pulling on that pair of electrons a little more than the other. And that means that that pair of electrons is closer to one of the elements than the other. So if I have something like hydrogen fluoride, fluorine has 1, 2, 3, 4, 5, 6, 7 electrons, and it's sharing this one from hydrogen. So fluorine has 8, it has an octet, it's happy. Hydrogen has the 2 that are being shared, it has a pair, it has paired electrons, it's happy. But fluorine is much better at pulling electrons toward itself than hydrogen is, because it has in its nucleus 9 protons. Hydrogen's only got 1. And so fluorine has a much larger nucleus that pulls, and remember, the nucleus is positively charged and the electrons are negatively charged. So fluorine has those 9 protons pulling on that shared pair of electrons. And what happens is that that shared pair of electrons spends a whole lot more time closer to fluorine than poor hydrogen. And so what we do is that in order to indicate this, we give a symbol, this little delta symbol. That means partial. And hydrogen is partially positive. It's not a full positive charge. It hasn't lost the electrons completely. But those electrons are spending a whole hell of a lot more time over in fluorine's house than in hydrogen's house. So we say the fluorine has a partial negative charge. And if you have more electrons spending time on one side of the bond than the other, we call that a polar bond. So we have a partial positive. It means it's not complete. It hasn't lost the electrons completely, but that pair of electrons is spending a whole lot more time in fluorine's neighborhood than hydrogen's neighborhood. So we have a partial negative on one side, we have a partial positive on the other side. And this polarity of molecules has a profound impact on how molecules interact. The reason that water is polar is basically why we exist today. I can get into more of that detail later. But it's incredibly important that some molecules are polar, some molecules are nonpolar. Nonpolar molecules like fats and lipids tend to stick to each other and form nonpolar interactions, and water forms polar interactions. And so water would rather be forming strong polar interactions with itself, and fats and lipids would rather be forming weak nonpolar interactions with itself because it can't form polar interactions with water. That's another reason why oils and water separate. Not just because they're different densities, because the way they interact with each other is totally different. And we'll learn why that is right now. So a polar covalent bond is just what I showed you a minute ago. Two atoms, one is more electronegative than the other. One pulls electrons toward itself much stronger than the other one. And so we have an unbalanced electron distribution. One is electron weak. The hydrogen is electron weak. There's very few. So if we were to draw it like a cloud, we would see we'd have very few electrons spending time around the hydrogen, and we'd have a lot more electrons spending time around the fluorine. So we'd say the fluorine is electron rich and the hydrogen is electron poor. That would be an unbalanced distribution. Now a nonpolar covalent bond, meaning that each atom has pretty much the same electronegativity. And you would see that if you had something like chlorine ion, a chlorine molecule. I have one chlorine, I have another chlorine. By definition, they have exactly the same electronegativity. One chlorine can pull on atoms exactly the same as another chlorine can pull on atoms. So basically, it's sort of like two huge sumo wrestlers pulling on a rope. If they're exactly the same size and exactly the same strength, that rope ain't going anywhere. So the distribution of electrons is exactly the same. They spend just as much time with this chlorine atom as they do with this chlorine atom. And so it's completely even distribution. That is non-polar. And so the reason why fats and lipids are so nonpolar is that they have a lot of carbon-hydrogen bonds. And carbon and hydrogen have almost the same electronegativity. So that's a nonpolar bond. Whereas polar molecules have a lot of like oxygens and fluorines and chlorines and nitrogens in them, which are more electronegativity than the average. And so you see a lot more polar bonds. So electronegativity, that whole term was invented by someone you probably have heard of, Linus Pauling. Linus Pauling was a very famous chemist. He also won 2 Nobel Prizes, but unlike Marie Curie, one of them was for chemistry and the other one was the Peace Prize. So pretty cool dude. So he made a measure of how strong an atom can pull electrons toward itself when it's in a covalent bond. And he ranked them from 0 to 4. Why he didn't do 0 to 10, I have no idea. But he's Linus, he's the man. And so fluorine is the most electronegative element there is because it has a relatively high number of protons to electrons, and so it pulls really, 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 really hard on electrons. So it's given 4 as being the most electronegative element, and then everything else is relative to fluorine. So again, sort of making the point, sharing equally is what gives you a non-polar covalent bond. And so that happens anytime the covalent bond has the same atom on either side, like with hydrogen or chlorine gas or bromine or iodine or nitrogen. Notice a lot of these are gases because they're non-polar bonding. There's not a really strong interaction between the molecules when you have non-polar interactions. I will get into the kinds of interactions between molecules a little bit later. But if you have non-polar interactions, those are weak. And so if you have very weak interactions between molecules, they tend not to stick together very well. And molecules that don't tend to stick together very well tend to be gases and liquids. Fluorine atoms are really, really electronegative. And basically, if they're bound to anything other than itself, it's going to form a polar covalent bond. So I've already showed you hydrogen and fluorine, but basically fluorine with pretty much anything, carbon, hydrogen, oxygen, it's going to form a polar bond because it's super, super, super electronegative. And so what you'll see is basically, you'll see where it's darker on one side than the other. That is the electron distribution. So these electrons are whizzing around, and we have that shared pair in here, and the shared pair is spending more time in the region of fluorine than it is in the region of hydrogen. So we have slight negative charge on one side and a slight positive charge on the other. And those positive charges will line up with actual positive and negative charges, and you'll get really strong interactions. We'll talk about those a little bit later as well. So the polarity of these bonds are determined in the difference between what the electronegativity of atom 1 and atom 2. And again, you do not have to memorize these electronegativities. There's a table in the list of all the stuff that you can refer to for a test. So they range from a low of like 0.8, which is rubidium, and the high is 4 with fluorine. Now notice there's a pattern here. Electronegativity goes down as the atoms get bigger and bigger and bigger. That makes sense because the bigger an atom is, the less that nucleus can pull on additional electrons. So look at fluorine. Fluorine has a really small nucleus, but the difference between fluorine with 9 electrons and having 10 shared electrons is just 1 out of 10. So it pulls on it rather hard. We have a really, really huge electron cloud like iodine. Iodine has 53 protons and 53 electrons. So the difference between 53 and 54, not that great. Difference between 9 and 10 is much greater. So iodine can't pull on electrons as well as fluorine can because it has all those other core electrons, those non-bonding electrons in the way that basically shield it from pulling on electrons. So when you get really, really, really big elements, those electronegativities go down. The other thing that happens as we go, metals have really low electronegativities because they're basically giving electrons away. They don't pull on shared electrons because they're giving them away. So they don't have high electronegativities. Their electronegativities are very, very low because they generally aren't sharing electrons at all. They're giving them away. And as we go across the periodic table from left to right, electronegativities go up. And that's because when you have just one more electron to get to a full set, that pull on that one electron is much greater than if you need to pull on two electrons to get to the full set. But you will see that the three most electronegative elements, well, four most electronegative elements are fluorine, nitrogen, oxygen, and chlorine. Those four are the highest, and everybody else is much, much less than those. So when we're trying to calculate whether or not something is polar or nonpolar, if the difference in the electronegativities of the two elements is around 0.4 or less, we say that's nonpolar. If the difference is greater than that, we say it's polar. And if the difference is really high, like above 1.5 to 1.8, we consider that ionic. So we can have really, really strong polar covalent bonds that we say have a certain amount of ionic character in them, because the electrons, the shared electrons, are spending so much time with one element than the other that it might as well be ionic, even though it isn't quite. So nonpolar, less than 0.4, polar, greater than that but less than 1.5. Then once you get like much greater than 1.5, we consider it an ionic bond. So let's put all of it together, looking at polarity of a bond and then the physical properties of molecules. Now we're going to use an arrow instead of just writing partial negative and partial positive. We're going to use an arrow to point in the direction of who's more electronegative. So everyone's familiar with this. We have a water molecule. The arrows will depict a dipole. What's a dipole? A dipole just has a large difference in charge density, where you have a partial positive and a partial negative. You have a dipole. And the arrow points to the more electronegative of the two. So with water here, we have an arrow pointing, so we have there's two different types of dipoles. There's a bond dipole and there's a molecular dipole. For the molecular dipole, we basically add all the bond dipoles together and see if they point in one direction or another. So let's look at the bond dipoles of water. So we look at oxygen, hydrogen. Which one's more electronegative? Well, oxygen is one of the most electronegative elements on Earth. It's oxygen. So this bond has a dipole pointing toward the oxygen. The other one is exactly the same, points toward the oxygen. Now, if I were to add those dipoles together, they're both pointing up. Notice they're both pointing up. They're pointing toward oxygen, yes, but they're also pointing up. So if I was to add them together, overall I would get a molecular dipole that pointed up. So is that a polar molecule? Yep, because if I add the two bond dipoles together, which are both pointing up, net, add it together, yes. It's the net, adding them together is also polar. Now, it's a little tricky of a concept, but let's look at carbon dioxide. So carbon's in the middle, and there's a double bond on one side, and there's a double bond on the other. Which one is more electronegative, carbon or oxygen? Well, it's going to be carbon. It's going to be oxygen. Oxygen is a lot more electronegative than carbon. You can check the numbers. Oxygen is like 3 and like carbon's like 2.1 or something like that. So oxygen's more polar. So There's the bond dipole in one direction toward that oxygen. There's the other bond dipole pointing toward the other oxygen. Now, because of the shape of CO2, we have exactly equal and opposite dipoles. They're each exactly the same size because the size of the arrow we make is dictated by the difference in electronegativity. If there's a big difference in electronegativity, I make a big arrow. If there's a small difference in electronegativity, I make a little arrow. But with CO2, difference between carbon and oxygen on one side is exactly the same as the difference in carbon and oxygen on the other side. So each of those arrows is equal and exactly the opposite. So when I add them together, they cancel. They're equal and opposite. And so CO2 is nonpolar, even though the middle is slightly positive and the outsides are slightly negative. It's completely symmetric. And if it's completely symmetric, it's nonpolar. Okay, we'll talk more about this in class. So let's have a look at some examples. So these are three bonds, not molecules, bonds. So I've got a nitrogen-carbon bond, I've got a nitrogen-oxygen bond, and I've got a phosphorus-fluorine bond. So I'm going to need a little more information. So what I'm going to need is the electronegativity table. So use the electronegativity table and then do the calculation, see what the difference is, and then see what kind of bond it is. Okay? So you can pause it here. So let's look at the differences. So nitrogen, where is nitrogen? Nitrogen is here. Nitrogen is 3.0. Carbon is right next to it, and carbon is 2.5. So the difference between 3.0 and 2.5 is 0.5. So that's right on the border of polar, nonpolar. So we would say that that is slightly polar. Not a whole lot, slightly polar. So we would draw and see which way would we do the arrow? Right, toward the nitrogen. And we would draw a small arrow. We wouldn't draw a big one. If we were doing the whole molecule, other bonds would probably have much larger differences and larger dipoles than that. So let's look at nitrogen and oxygen. So nitrogen, we know already, is 3.0. Oxygen is 3.5. So again, that's a difference. We say delta for difference of 0.5. So we would say En for electronegativity difference 0.5. So again, that's polar but not super polar. So we have our nitrogen, our oxygen. Now which way would the arrow point? Right, towards the oxygen. And again, small arrow. Now the third one, I have phosphorus and I have fluorine. So fluorine is super electronegativity of 4. And phosphorus is 2.1. So the delta electronegativity there is 1.9. So big difference. So that is bordering on ionic, even though both of these elements are non-metals. So we would say that that is an extremely polar bond. So when I have phosphorus and fluorine, I would put a large arrow pointing towards the fluorine, because that is super polar bond. That's like about as polar as it gets, without being ionic, because they're both non-metals. So the difference in the size of the arrow indicates how polar it is. So that would be small. Oh, you also want to give it a little cross here. I neglected to mention that. That helps determine which side is polar, because this little cross here basically tells you which side is going to be partially positive. The phosphorus is going to be partially positive. The fluorine is going to be partially negative. So we put the little arrow there to indicate which is positive. So a small difference would look like that, and then a large difference would look like that. So that's when you're looking at the molecule. If you're adding together something that's this small and something that's this large, then you can see that they wouldn't cancel. If they were pointing in equal and opposite directions, they wouldn't cancel out, because this arrow is much bigger than the other one. And so it would still be polar overall. So let's look at some of the characteristics of these molecules. And this we've talked about already, because I really, really want to make the point of what a mole is, right? So we know the molecular mass is just adding together the masses of all the atoms in a molecule, and you sum them all together. Now, the molecular mass of atoms is given in AMUs, or atomic mass units, which are useless to us because we can't measure atomic mass units without a very, very, very expensive piece of equipment, one of which I used to have back at UCLA that cost, about $1 million. Something like that, you can actually measure atomic mass units. But it takes an instrument that costs you about $1 million in order to do that. If we don't have an instrument that costs $1 million, that's called a mass spectrometer that actually directly measures the mass of atoms. We have a scale that we can afford that measures in grams. And so we use a unit called the mole that relates the AMUs, atomic mass units, to a gram that you can actually measure. So the molecular mass is the mass of 1 mole. So it is just the average atomic mass that you can find on a periodic table in grams per mole. So AMU is also equal to grams per mole. And it's grams per mole we're interested in because we can measure grams with something that doesn't cost $1 million. So let's calculate the molecular mass of a couple of these things. So I'll give you a minute. You're going to need your periodic table and a calculator of some kind. Give you a sec. Okay, so we look up the masses, the average masses on our periodic table. So we look up sodium, and we see that sodium atom has an AMU of 22.99. What does that mean? It means that 1 mole of sodium atoms equals 22.99 grams. Perfect. And chlorine atoms has an atomic mass of 35.453. Now that's from the periodic table I have. You can look up greater, more accurate mass. If I don't tell you the actual accuracy I want, then look up whatever numbers you want. It could be like 23 and 35. Generally, we use all the numbers that are present on the average mass on the periodic table. So when we add those together, I get 58.443 grams per mole. But How many significant digits should I use? Well, I'm doing addition this time, right? So sodium, I've only got a mass of 2 digits past the decimal point. So I can only give an answer with 2 numbers past the decimal point. So I would round that to 58.44 grams per mole. Okay? Now, that means that a mole of sodium chloride has a mole of sodium and a mole of chlorine. So if I know the mass of sodium chlorine, I know the mass of the compound sodium chloride. So next, good old dihydrogen monoxide. So when I look up the mass of oxygen, I know I have 1 mole of oxygen atoms in a mole of water. Oxygen is 15.999 AMUs, or grams per mole. And hydrogen is 1.008 grams per mole. But there's 2 of them. So that comes out to 2.016. So I add those 2 together, and I get 18.017 grams per mole. So look at it this time. Since I'm adding them, I have 3 decimal places past the 0 for this. I also have 3 decimal places past the 0 for this. So I can use all those digits. So 18.017 grams per mole. And that's probably something we're going to be using a lot, because there's, remember I mentioned hydrates at the end of the previous section. So the mass of water, you might as well memorize it. It's around 18 grams per mole. Oxygen is 16, hydrogen's 1, so it's around 18. Now we're going to look at shapes for a minute. And we'll deal with this a lot more in class and during the work sessions, because this is a really, really important concept to learn. Now, it's given this weird name, Vesper. I don't know, it sounds like an evil supervillain from the Marvel universe or something. But all it means is pairs of electrons, since they're negatively charged, will repel each other. That's it. That's really all you need to know about this particular theory. And that makes sense, right? Electrons are negatively charged. You put 2 negatively charged things together, they're going to repel each other. So also it means that we need to think about electrons in space. Where are the electrons in space? Electrons are going to be in 2 places. They're going to be in bonds, or they're going to be in lone pairs. The rest of the electrons are going to be closer to the nucleus of the atoms. The core electrons, the non-bonding electrons, those are going to be closer to the nuclei of the atoms, and so don't really influence the shapes very much. But lone pairs are going to be out in space, a little bit further away, because they're far away from the nucleus, because they are bonding. They're in the bonding region. And bonding electrons themselves are obviously between 2 atoms. They're going to be farther away from the nucleus. So what molecules will do is generally take shapes to maximize the distance between them. So if I have a pair of bonding electrons here in space, and I have a pair of bonding electrons here in space, what's going to happen is this molecule will take a shape to maximize the distance between them, because they're both negatively charged. So they're going to push each other away. And we'll find that lone pairs are even better at pushing other electrons away. And that makes sense, because at the end, with a lone pair of electrons, I just have 2 electrons with no nuclei around, with positive nuclei. So that is more negative than a bonded pair. That has an even bigger influence on shapes of molecules. But really all it means is that electrons in space, bonding and non-bonding in lone pairs, want to get as far away from each other as possible. And so molecules will adopt a shape that allow them to do that. So let's look at an example. So we looked at methane a little earlier. Methane is just a single carbon in the middle, surrounded by 4 hydrogens, 4 single bonds, super simple molecule. Now, also mention that, if you draw it, it just looks flat, right? And the bond angles, since it's flat and there's 4 bonds, go around in a circle. That's 360 degrees. And so I have four of them. That's 360 divided by 4. It's 90 degrees. So each one of those bonds should be 90 degrees. But we can actually look at the angles of those bonds. We can calculate the angles of those bonds, and we can actually look at them by shining light on these molecules. They reflect and they absorb light depending on the bond energies between them and the shapes. And when we do that, we can see that the actual bond angle, the angle between a hydrogen, a carbon, and another hydrogen, is actually 109.5 degrees. It's not 90 degrees. That tells us that this is not a 2-dimensional shape. It's a 3-dimensional shape. And that 3-dimensional shape is a tetrahedron. It's like it's a tent. These things are bent. They're not straight. And that makes sense because if they're at 90 degrees from each other, those hydrogens are actually closer together than they would be at 109 degrees. At 109 degrees, instead of being this close together, they're that close together. They're further apart. And so there's less repulsion between those bonding electrons. If I go from here, it's one distance. If I go to there, they're further apart. That makes sense, hopefully. So if you want to draw what that actually looks like, we use what are called wedges and dashes. A wedge means it is in front. So I draw this little wedge. So here's a hydrogen, here's a carbon. That means that hydrogen's coming out at you. Whoa. So just like in 3D, it looks like it's coming out of the plane. Now I draw this dash to look like it's behind the plane. And then these single lines would be in plane. So this particular diagram, I have this bond is in the plane, this bond is in the plane, this one comes out, whoa, that one comes out, and this one goes behind. That indicates that it is a 3-dimensional structure, not 2-dimensional. It is not flat. It is actually in 3 dimensions. So determining the shape of a molecule, we use this VSEPR. You won't have to remember VSEPR. All VSEPR means is just electrons like to be apart. That's all it means. But there's certain rules we have that if you know what the rules are, you can basically just look up what the shape is. And again, if I haven't included this in Canvas, I will put it in there. I've like a couple of really nice sheets that give all the different shapes a molecule can have based on these rules. So all you need to do is figure out what is the central atom, what atom's in the middle. Figure out how many bonds it's making, how many bond groups it's making. So a single bond and a double bond are both considered a bond group. Why? Because they're both electrons in space in the same area. So if a carbon is making a single bond with a carbon, it's sharing 2 electrons in the space between those atoms. If it's making a double bond, it's sharing 4 electrons but also in the space between those two carbons. It's not like they're sharing them off in the distance. You can't share something if it's not between the two atoms. And so same with a triple bond. Now 6 electrons are being shared, but where in space? Well, between the two carbon atoms. That's where they need to be. So that's why we call them bonding groups or bonding regions. And so you need to identify how many of them there are. In this instance, each one of them would be considered one. That's one bonding region. The single, that's one bonding region. It's a double, but it's between the two carbons. And this is also one bonding region. It's a triple bond, but it's still between those two carbons. So we call that X. So the central atom, we write down as an A. The number of bonding regions around that central atom we represent with X. And then the number of lone pairs around the central atom we represent with an E. So unfortunately, it's like Axe body spray, really nasty. But we use this to figure out how many bonding regions and how many lone pairs. So we put a number here and we put a number here. So we have to identify three things. Who's the central atom? How many bond regions is it making? How many lone pairs does it have? And then when we figure out A, X, and E, we can figure out what shape it is. Let me give you some examples. So here's what some of those actually look like. And these are weird sounding names. You may have heard of some of them. You may not have heard of some others. Let's look at the first one here. So in this instance, our central atom is, we always just refer to it by A. It doesn't really matter what it is. We just need to know which one is the central atom and then how are things arranged around it. So in this instance, we have a central atom. We have a bonding region on one side and we have a bonding region on the other side. So A, X, E, it has 2 bonding regions and it has no lone pairs. So that's just AX2, and that would be linear. Now, an example of that would be carbon dioxide. Now, carbon dioxide does have lone pairs, but all the lone pairs are on the oxygens. There's no lone pairs on the carbon. So in that instance, carbon is the central atom, so that's A. It has 2 bonding regions. They're both double bonds, but there's only 2 regions, one here and one there. So AX2, and carbon has no lone pairs. So AX2. That's why carbon dioxide is a linear molecule. Okay? Now let's look at another one. So the next one is A is, again, central. It has 2 bonding regions. 1, 2. But it also has a lone pair. So E. So we look up what that would be. Now, for instance, we could look at that as water. Water would look like this. Oxygen has 1, 2 lone pairs, and a hydrogen here and a hydrogen here. So A is the oxygen. It has 2 bonding regions, and it has 2 lone pairs. 1, 2. So what kind of shape is that? That is bent. That's why it isn't linear. You would think that oxygen, since it has 1 hydrogen on one side, 1 hydrogen on the other side, that would be a linear molecule. But you need to take into account the lone pairs it has too. Now those lone pairs push the bonding electrons away from it and causes the whole molecule to be bent. So again, you do not have to memorize this because I will give you a table with all the shapes in it. What you need to do is be able to identify what the central atom is, how many bonding regions are around it, how many lone pairs. So let's look at different ways we can represent them. So non-bonded pairs, like lone pairs, they take up space, but we can't see them. They're invisible to the shape. We can only see the atoms. We don't really see the electrons. Why? Because atoms are much bigger than electrons, remember. Electrons are super, super, super small. So you can't really see them. So you see something like nitrogen, and nitrogen has 1, 2, 3 bonding regions. So it's A, X, 3, E with a lone pair. Now that gives you a pyramidal shape. But when you actually look at the shape itself, we don't see the top of the pyramid. We just see that it's bent. We just see that the hydrogens are bent down a little bit. So when we draw this out, it looks like that. Okay. Same thing with water. I just showed you a minute ago. It's the same shape as ammonia, but we just replace one of the bonded hydrogens with a lone pair. And so we wouldn't see that as pyramidal, but overall it is pyramidal, but we just see the oxygen and the 2 hydrogens. So to us it looks bent. Okay? So bonded electrons are confined between those 2 atoms, but non-bonded electrons aren't, and they take up more space. And they're more negative because they don't have an atom, a positively charged nucleus on the other end of it. So they take up more space and they push away atoms better than other atoms do. So you can see that in the difference of the angles. So with ammonia, the angles between the hydrogen atoms are 107 degrees. But with water that has 2 lone pairs that push them even further away from the lone pairs and closer to each other, the bond angle is only 104. And the difference is the additional lone pair, which takes up more space and pushes those other electrons further away from it. Right, let's have a look at these. I'll give you a second to figure it out, and then we'll do it together. All right. So since you have the picture, you don't even have to figure out what's the central atom. If you had a formula, you'd have to figure out what the central atom is. So here I have silicon in the middle. So A is my silicon. I've got 2 bonding regions. I got one here, and I got one there. Even though they're double bonds, remember, it's still a bonding region. So I have AX2. And how many lone pairs on the silicon is there? None. So it's just AX2. And if we look up what that is linear. All right, next one. We have central sulfur, and we have hydrogen on the other. So hydrogen sulfide. That is super, super stinky stuff. So sulfur is in the middle. It has 2 bonding regions, one here and one here. But it also has 2 lone pairs, one there and one there. So that should look like water. and it is bent. It looks like water, but sure as hell doesn't smell like it. And then finally, we have the last one. What would be the name of this? That's right. It would be phosphorus tribromide. So I've got phosphorus in the middle and 3 bromines around it. So A, X, 1, 2, 3, and no lone pairs. So what shape can that adopt to give the maximum distance between those bromine atoms and the bonding electrons in space? That would be a plane with 120 degrees between each one. That gives you the maximum distance. And so we call that trigonal for 3 and planar. So the trigonal planar molecule. So again, I will put this table in Canvas if I haven't put it there already. I'll need to double check. And we'll do a lot of these together in the work group. All right, I will see you tomorrow.